In this lecture, I'm going to discuss some different strategies for doing group-level statistical analyses. But actually, I'd like to start with two slides that I meant to put in the stats intro lecture, but somehow forgot accidentally. So this first point I'd like to make is about the distinction, or I should say dissociation, between within-subject statistical analyses versus group-level statistical analyses. At the within subject level, what you're really concerned with is the relative size of the effect to or compared to the variance of the data over trials. So this is when you're doing statistics like within a single individual. When you do group level statistics, so now this is statistical analyses done over pooling data across 15 or 20 or 50 subjects. Now what you're really looking for is the consistency of the effect, or the direction of the effect, across the individuals within your group. And within subject variance doesn't actually matter, so it doesn't get taken into account in group level analyses. So this means that so the variability over trials doesn't get into the group level statistics. It can, of course. There are these multi-level modeling or hierarchical models that allow for individual variance to be taken into the group level. So this is not sort of necessarily always the case, but this is like 99.9% of the group level analyses that you see in psychology, neuroscience, and cognitive neuroscience involve ignoring the within subject variance in order to focus on the consistency of the effect across the individuals. So let me illustrate pictorially the distinction between within subject statistics versus group level statistics. So I'm going to present three situations that will show this distinction. Here's the first situation. So you have single subject effects and a group level effect. And here, so on the y-axis, this is just, some measure of effect size, something that's sort of arbitrary. And here now you imagine that each one of these is a subject. So we have 6 subjects in this experiment. I know it's not many for group level analysis, but you get the idea. So you can imagine these distributions are showing the distributions of trials within each subject. So these would be all the trials for this subject and all the trials for this subject. So we can say that all the trials are greater than 0, or the data is greater than 0. So let's say there's a significant effect within each subject, and also there's an effect at the group level. Now at the group level, you're generally not taking into consideration all of the variance across trials here. You're really just looking for the mean response. So you would just take this data point and this data point and this data point. So at the group level, typical group level analyses, you would only have 6 data points. And really what you want to see is whether these 6 data points, 1 per subject, are consistently above 0. Here we have situation 2. So here we have effects within each subject individually, but no significant effect at the group level. So here you see all the individual subjects are far away from 0, but we have 3 subjects below 0 and 3 subjects above 0. So there is no group level effect in this case. Now, of course, maybe this is meaningful. If these were like, maybe these were the control subjects and these were subjects who took a medication, so maybe this makes sense. But, just taking a very simplistic look, we can say here there are single subject effects and no group level effects. And here in situation 3, we see that there are no individual or within subject statistically significant effects, but there is a significant group effect. So if you look at the individual subjects, you can see the distributions are all overlapping with 0 quite strongly. So let's, I'll talk more about error bars later, but let's say that this effect is not statistically significant at 0.05 within any individual subject, but the group level analyses, you're only concerned with the average response over all the subjects. And you can see that that average response is positive for 6 out of 6 subjects, so we would still get a pretty strong group effect in this case. Okay, so the point of this is that within subjects and group level analyses are both insightful, they're both informative, but you shouldn't confuse the two things. It's not necessarily the case that if you have a group effect, then all of your individual subjects should show the effect as well. That would be situation one, which is, it's pretty powerful if you can show this, but depends a bit on the effect size and so on. Okay, now let's talk more about group level analyses. So now imagine we have 12 subjects, and here we have time frequency plots from each of the 12 subjects. So actually, if these were really, it's a little bit noisy. I think these might be single trials from the same subject, but that doesn't matter. So pretend that these are time frequency plots from 12 different subjects from the same condition. And now the question is, what do we do? How do we do our statistical analyses to see what patterns of time frequency dynamics are consistent over these 12 subjects? So now I'm going to introduce you to 3 different strategies for doing group level analyses on time frequency data. So approach 1 is using non-parametric, or I should say permutation-based statistical testing. This is actually the same exact thing that we discussed in, 2 lectures ago in the permutation testing lecture. But now we use the average of trials across subjects rather than individual trials within a subject. So that is to say, the thing that we're permuting is not individual trials across across conditions within the subject. We're permuting these different maps across subjects. And here again, this is like what I said in the beginning of the permutation lecture. You have to think about what is the null hypothesis and how do we go about testing this in the null hypothesis in our data. So this is not always so simple to figure out how to create a distribution under the null hypothesis. It depends a lot on exactly what you're looking for. So if, for example, I'll give you one example. Let's say that these are maps of condition A minus condition B for each subject. So this is A minus B subject 1, A minus B subject 2, and so on. So now if we think that, if we say that the null hypothesis is that there's no difference between condition A and condition B, then that null hypothesis predicts that we can say A minus B or B minus A, and those would give us exactly the same results, right? Because A and B are the same. So the way we could turn this around, if each of these maps represents A minus B, would be to multiply for any individual subject, or I should say pick a random subset of subjects and multiply the entire time frequency map by -1. So the effect, so now, this is like super complex algebra here. So if we say A minus B, and we want to turn that into B minus A, we can just put a -1 in the front, and that gives us, that reverses the sign. So you do that for a random subset of subjects, and that would be the way to do permutation testing on maps reflecting a condition comparison of A minus B. Now you would not want to pick a random subset of pixels and multiply those by -1. That's inappropriate because you're changing the smoothing characteristics, the temporal and frequency autocorrelation characteristics of the data. So you would just want to take the entire map and multiply it by -1 for some random subset of subjects. And then you would compute the difference map, and that would be one iteration in permutation testing. Okay, so some advantages. So I'm not going to talk about this anymore because you already know how to do this kind of permutation testing. So advantages, you don't need to worry about any assumptions of parametric statistics, like I discussed previously. All the analyses are performed within Matlab. You don't need to interface with other software programs. I'll get back to why. You'll understand this point in a few minutes. There's little concern for user bias or potential way to interact with the statistics or to bias the statistics. I'll also talk about this a bit more later on. And in fact, I think the next lecture is going to be all about circular inference and avoiding circular inference, aka double dipping. So it's open to exploratory analyses. If you don't know exactly which time frequency regions should be might be related to your task. This is nice. You can sort of test everything and see what happens to come out significant. And of course, it's also amenable to multiple comparisons corrections, as discussed in the previous lecture. Some disadvantages of this is that this approach is really optimized for testing two conditions, or for testing a bivariate correlation, let's say, between task performance and brain activity over a group of 30 subjects or something. This is not really a good approach for doing a full factorial design. If you have some 3x2 ANOVA, lots of different conditions, different levels, different factors. This kind of simple permutation testing approach is not really well suited for these kinds of statistical analyses. And then I also say that a disadvantage is that it's open to exploratory analyses. This is, you want to make sure that you are doing, that your analyses are at least, somewhat driven by theory and ideas and hypotheses and so on. So you shouldn't be just sort of testing everything that you have in as many ways as possible. That's going to inevitably produce alpha errors or results that are difficult to interpret. Okay, so that was approach one. Then the next two approaches kind of one. So I broke it into approach 2A and 2B. 2A is where we take a time frequency window and we average the activity within that window. So it would look like this. Imagine this plot is a time frequency power plot, and this would be the average of all the conditions versus baseline. So it could be like decibel normalized or whatever. But actually that versus baseline thing is not the critical point here. The critical point here is that this is the average of all the conditions. And then we look and we see where are the sort of main task responses in time frequency space. And then we draw a box around those, and then we can average all the pixels within this box, or this can be some region that's defined based on significance, significant change from baseline or something. So then this would be this is like a more manually driven selection. This would be more sort of data driven selection. So then the idea is you average all the results within all of the pixels in this time frequency space, and then you extract it separately per condition. So here would be the response for condition 1 and the response for condition 2. It's important in this case to make sure you're drawing this box in a way that's orthogonal to the actual condition contrast that you want to investigate. That's to avoid something called circular inference or biasing your statistical analyses, and I'll talk more about that in the next lecture. Right, so now we have this table. So we have different subjects and we have the different conditions, maybe a few different time frequency windows. And this, by the way, would be a case where Bonferroni correction would be appropriate to apply. So if we wanted to test whether there is an effect in the delta band and test whether there is an effect in the beta band, here we have two time frequency windows, and so it would be appropriate to apply a Bonferroni correction in this case, and then so then you would use a p-value of 0.025. So how big to make this window? It should be something that looks reasonable. I try to imagine that I am a critical reviewer looking at this anonymous scientist who is picking this window. And if I were a critical reviewer, would I think that this is an appropriate selection of a window? So in this case, I would say, yes, it looks fine. Maybe it could be a little bit smaller, but I don't think that there's anything weird. This doesn't seem suspicious. It doesn't seem inappropriate. It doesn't seem hastily and thoughtlessly done. So now then this window is based on the group level analysis. So this would be time frequency power plot averaged over all subjects and averaged over all conditions. And now, so this is what I already described in the 2 slides ago. Now you take this window and you apply it back to each subject. and then you get all the data points within this time frequency window. And then you would average over all these separately per subject and per condition, and then put that into a table, which then you can analyze in some program. You can already see that you can already see the main disadvantage of this method, which is that because this window is based on the group average, it's necessarily not going to be optimal for every individual subject because there's individual variability. So here you see this window is not really great for this subject. It's not really great for this subject. It seems okay for some of these other subjects. So this is there's always trade-offs, I guess. This is one disadvantage here. So now the idea is you can export this data file that you got from Matlab and import those data into, in this case I'm showing SPSS or Excel or R or SAS if anyone still uses that, or any number of other kind of standard psychology or sociology, behavioral statistics software packages. This is useful. This can be nice because these different so SPSS, for example, is much more suited for, designed for doing things like mixed effects, ANOVAs, and things like that. So some advantages of this method: you can use kind of standard parametric statistics that you might be used to if you have a psychology or statistics background. So then I should mention that although some measures of brain activity are definitely non-normally distributed, other measures of brain activity are normally distributed under the null hypothesis. For example, decibel normalized or percent change normalized power, so if you compute relative power, that is, it has a pretty normal looking distribution under the null hypothesis. So particularly if you're taking time frequency windows like this of normalized power, the results often do conform to assumptions of parametric statistics. So you can also use software that's specially designed for statistics, and this allows for kind of more full factorial or flexible statistical designs. It's very hypothesis driven. Once you carve out this window and time frequency space, it's appropriate to use a p-value of 0.05, and you don't necessarily need to correct for multiple comparisons unless you are actually doing multiple comparisons like multiple frequency bands or multiple electrodes and so forth. But this means, so hypothesis driven means it's more sensitive to finding real and perhaps subtle effects. And this is in part because you don't need to worry about multiple comparisons. Again, so of course sometimes you do, but you don't need to worry about multiple comparisons over tens of thousands of time frequency points. Some disadvantages is that it's potentially open to some selection bias in choosing the time frequency windows. But this is actually very easy to avoid if you're, sort of thinking carefully about this. I'll talk more about this in the next lecture. I think one disadvantage is that it involves more software programs, more data files, more opportunities for confusion. This may not sound, this may sound a bit stupid to say this, but it really is true that if you're exporting text files from Matlab and then you give them different names, and then you have to import different files into SPSS and make sure that you got the right one, it can get confusing, and there's certainly an opportunity for increased confusion and, for example, accidentally running the analyses on the wrong data file that you exported from Matlab. So just something to be mindful of. Okay, so that was approach 2A. Approach 2B, you might guess, is very similar to approach 2A. I think the main disadvantage of approach 2A is that you're constrained to using the exact same time frequency window for all of the subjects and all the conditions. So the idea of condition of approach 2B is very similar. So now you still draw a window at the group level. So this would be the time frequency power plot averaged over all the conditions and averaged over all the subjects. But now the idea is to draw a bigger window, and you apply that larger window to each individual subject, and then extract within this larger window. Then you find a smaller window within each subject that where there's the largest response, or the largest negative valued response if you're looking for a suppression. So this has two advantages over method 2A. One is that it's a bit more sensitive to the individual subject variability. So you can see this subject has a slightly higher frequency response. This subject has a somewhat earlier and lower frequency response. So that's one advantage. It's a bit more sensitive to individual differences. And a second advantage is that it also allows you to very easily incorporate peak frequency and peak time point for each subject. So this might be relevant if you want to correlate the peak frequency with, I don't know, some measure of brain structure or whatever. You want to correlate across subjects the difference in the peak timing with, I don't know, their height or something. Age, maybe that would be a plausible thing to correlate with peak timing. Okay, so this kind of it gives you increased sensitivity for individual differences. So here we drew this larger window, and now you can see that this window is more custom tailored. So the window being applied to each subject is more custom tailored to identify the best window for each subject. That said, so it's more sensitive to the individual variability, but it's also at the same time more sensitive to noise. So that's one disadvantage. If you have really noisy data, if this is like data were collected in patients or something, and you don't have a lot of trials, then the data tend to be a bit noisy at the single subject level. So there is a danger that this approach, that this window can go towards, a little peak of noise rather than the real-time frequency dynamics that you want. So anyway, there's of course advantages and disadvantages of every statistical method. I believe the advantages here are all the same as for method 2A, with the addition of being able to test subject-specific or condition-specific timing or peak frequency responses. And I think the disadvantages are also the same as 2A. So, shall we have a look at this in Matlab? So, what we have here, you can download from the website these data files. There are 6 data files. These come from a really old experiment. I don't even remember I think it was just even pilot data for when I used to teach an earlier version of this course. Anyway, doesn't matter. So what I'm going to do here is introduce you to the general format of the group level analysis scripts that I typically write. So of course, this is like it's a model, so it's not really very detailed, but this would be sort of give you inspiration about how I go about writing group analysis scripts. So here we find a list of all the subjects. So these are the subjects. This would be, each one of these files is the output of a level 1 analysis that would do, for example, time frequency analyses. So here we want to load in each subject's data. So we loop through subjects, load in that subject's data, and then enter that subject's data file into this large multi-dimensional matrix in which we're going to store all of the single subject data in one matrix. Here's where it gets initialized at the first subject. And in practice, if you have multiple analyses that you did, you might have more of these things. So let's inspect the size of the... So this is a subjects by conditions, by channels, by frequencies, by time points, and I think this was power versus intertrial phase clustering. So it's quite a big matrix. It's a 6-dimensional matrix, but you'll see that storing your group level analyses in this way makes it really convenient for just averaging over subjects, for example. Now we can just average over the first dimension. So that's very easy. You can also see, this is really why it's helpful to temporally downsample your results and not to extract too many frequencies if you don't need to. If we had the full time resolution, which is maybe like 2,000 data points, this matrix would be ginormous and maybe even too big for Matlab. Okay, so now the idea, again, this is how I organize my group level analysis scripts. So I would have one cell like this, and each cell would do something. It would do some group level statistics, maybe some permutation testing, or it would plot some data across all subjects. In this case, I'm going to plot time frequency maps for this channel, so for C4, and here I define color limits. I'll let you go through. Actually, none of this code is really very new to you, although the variables have different names from what I've since adopted. But the important point here is you can see here's this TF-all matrix, and now I'm going to average over the first dimension, which is subjects. So now just by running this cell, we get these very nice time frequency plots of power and ITPC, and this is averaged over our huge group of 6 subjects. So here's another one. I won't go through this cell in much detail either. You can look through it on your own. But the important point is that we are looping over time points, and we are looping over conditions, and we're going to make a topographical map. And again, you can see here we're taking the mean over the first dimension, this over the first dimension, which is subjects. And now here we're also averaging over the 4th dimension, which is 1, 2, 3, 4. So that's averaging over frequency windows. We could also average over time windows here. So now we run this, and now we get some nice topographical maps for average over subjects for different time points. And I think this experiment was like there was stimuli on the left side of the screen and the right side of the screen and the center, and the subjects just had to press their different hands or something like that. I don't know. That doesn't matter for now. Okay, now in this cell, performs method 2a. So we are going to define a time frequency window. In fact, here I'm defining 2 time frequency windows, both in the theta band, and one earlier and one later time window. And I'm going to extract data for 4 different channels, and I'm going to store the data file into this text file called statistics file. So it's a very aptly named file. And so here is quite a lot of loops down here. It ends up being like 5 nested loops, which is quite a lot. And the main part of this cell is here, where I use this function fprintf to export the data from this subject and this condition and this channel and this frequency range and this time range. You can see it's quite a mess actually. And it's going to put that all into one file along with some handy labels at the top of each column to indicate what's going on in that data. Well, I'll let you inspect this code at your leisure, and you can see that this text file is going to be something that you can now import into Excel or SPSS or whatever. In the interest of time and I guess risk of boredom, I don't want you to get bored. I'm not going to go through this file, but this cell does method 2b. So it's a very similar thing, except now from this big window, you can see I drew this big window from 200 to 800 milliseconds and 2 to 10 hertz. And it's somewhat similar to the previous cell, except that within each subject, we have to find So we have to create this like smaller matrix of data, which is only the data inside that time frequency window. So 2 to 800, 200 to 800 and 2 to 10 hertz. And then we find the maximum point within that window, and then that's what we use to extract the data. So it's a little bit more involved, but you can look through this line by line. I should issue a strong caution here that this is code that I wrote specifically for these data. So I really do not recommend just blindly copying and pasting this code and using it on your data. Just changing a few things up here and running it. So please do not do that, because it might work, but I can't guarantee it. It also might not work. So if you would like to use this this code for your data, go through it line by line, make sure that it's going to do the right thing for your data set, and do some sanity checks and make sure that it's really giving you accurate results. So that's it. I hope you enjoyed learning about group level analyses. The next lecture, I'm going to follow up on this issue of selection biases and circular inferences.